Welcome back to the deep dive. Today, we're tackling something pretty fundamental for large language models. How do we get them to be, not just better reasoners, but also to actually know when they're reasoning well, and crucially, to do that efficiently?
Right, without grinding everything to a halt.
Exactly. We've seen huge leaps in LLMs, especially with complex logic. A lot of that is down to RLVR reinforcement learning with verifiable rewards, which basically rewards the model if its reasoning leads to the right answer, checked by some external verifier.
It's a solid training approach, definitely.
Right.
Rewarding based on external truth. But, and this is the big but, it creates a major headache later
What's
on.
actually deployed?
Yeah, at test time. Suddenly there's no answer key, no ground truth. The model might give a brilliant answer.
It has no idea if it's brilliant.
Precisely. It lacks that internal confidence check, that self-verification signal. And it's a huge problem for using these things reliably. You need that calibration.
Absolutely. If the model can't gauge its own accuracy, how can we? And the old ways of fixing this, they weren't great, were they?
Not really. They were mostly clunky and, frankly, expensive. You either had to train a whole separate LLM just to act as a verifier.
Like hiring a second massive brain just to check the first one's homework?
Right. Or the other way was to make the same LLM do both jobs, but one after the other. Generate the answer first.
Then prompt it again differently to make it reflect on its own answer.
Exactly. Sequentially.
And that sequential process running 2 full inference passes, well, that just kills efficiency. Our sources say it can basically double the cost for every single output.
Yeah, double the compute time, double the cost. Just not scalable.
So what the field really needed was a way to merge these things, generation and verification, without that massive overhead.
And that brings us right to the heart of today's deep dive. This algorithm called LaSeR. It stands for Reinforcement Learning with Last Token Self-Rewarding.
Yes, sir.
And the promise is that it tackles both the verification problem and the efficiency problem head-on. It finds that confidence signal right at the very end of the generation process.
Okay, this is where it gets really interesting, sort of technically and conceptually. The LaSeR researchers had this hunch, right? That the model's self-assessment, its own feeling of, yeah, I got this right, or, not sure, didn't need a whole separate thinking step. They figured it was already there, somehow encoded, just as the model was finishing its thought, like in the final moment.
That's the core insight, yes. And they actually found the mathematical proof for it. They derived a closed-form solution from the underlying RL theory.
Okay.
And it showed this really elegant equivalence, the true reasoning reward, the one based on the external verifier, let's call it TRSCA.
Right, the objective truth signal.
Is mathematically equal to an internal score the model generates itself. They call it the last token self-rewarding score.
Yeah,
Right.
hold on. So the external score, 40 lowers, which takes effort to calculate based on the answer, is perfectly mirrored by this internal score that the model just produces.
That's the claim, yeah. It's like the model leaves itself this instantaneous little note about its confidence.
A secret confidence signal. But what is that signal? Is it a word?
No, not a word. It's purely statistical. It's derived from the log probability, basically, the likelihood that the model assigns to a specific pre-chosen special token right after it finishes its actual answer.
A special token, like a placeholder.
Exactly. Could be anything like vision start or some reserved token code. The model finishes its answer, say the answer is 42, then it calculates the probability of the next token being, say, special confidence token.
And a high probability for that special token means high confidence. Low probability means low confidence.
That's the idea. It's measuring the model's internal state via that next token prediction.
Okay, but calculating these RL scores usually involves comparing the main model to a reference model, right? Which sounds computationally heavy again. Where's the efficiency game?
This is the clever part. The full theoretical calculation does involve that reference model component. But the researchers noticed something crucial empirically.
What was that?
For this specific kind of special token used for the self-reward score, the log probability assigned by the reference model, well, it barely changed. It was practically a constant value across different problems, different solutions.
A constant, really?
Yeah, like for the Quint models they tested, this value, let's call it a craft, was consistently hovering around -23.0, a very small, stable number.
So they could just plug that number in.
Pretty much. By approximating that reference model log probability as a pre-calculated constant, they could sidestep the need to actually run the reference model calculation during the score computation.
Wow. So they just subtract this constant value, roughly -23, instead of doing a whole massive model forward pass.
That's the essence of the efficiency gain. It cuts the computational cost for getting this score practically in half. It's a really neat shortcut based on an empirical finding, but it saves a ton of compute.
That's genuinely clever. Okay, so the theory is that this last token signal reflects the true reward, and they found a cheap way to calculate RLR. How do they actually train the model to make TORs accurate?
Well, instead of adding a whole complex RL optimization loop just for self-verification, they use something much simpler. Squared error loss, MSE.
MSE loss, so just mathematically forcing two numbers to get closer together.
Exactly. They add an MSE loss term to the standard RLVR training objective. This extra loss simply pushes the model's calculated internal score to a ways to be as close as possible to the true external verifier score, 4VIR, for each training example.
So it learns to align its internal feeling with the external truth.
Right. It optimizes for both generating the right answer and generating an accurate confidence score for that answer, all in one combined training process.
Okay, let me push back a bit here. The external verifier, the source of TOR values, might not be perfect, right? Especially for complex reasoning, it might be rule-based, maybe a bit rigid.
That's a very fair point.
If you're just using MSE to force the internal score zeroers to mimic a potentially flawed RVAL, aren't you just teaching the model to inherit the verifier's flaws in its confidence signal?
That's a critical concern, and they did think about it. The way they integrate these scores back into the main RL training helps mitigate this. They calculate something called self-rewarding advantages based on how... And then they combine these self-rewarding advantages with the standard advantages calculated from the external verifier using a weighting factor, tau.
Ah, so it's a mix. The model's own judgment gets blended with the external judgment.
Exactly. That blending, controlled by tau, allows the model's internal gut feeling to sort of smooth out the sharp edges or potential errors of the external rule-based verifier. It allows for more fine-grained learning using the model's confidence as part of the feedback.
That makes sense. It stops the model from just blindly copying a potentially imperfect teacher.
Right. It introduces a bit of self-correction, you could say.
And let's just circle back to the efficiency again, because it's so important. With LaSeR, the model generates its answer and then calculates the score.
All in a single forward pass. The extra cost is minimal, just the computation for at most one additional token prediction.
One extra token prediction versus potentially thousands in a whole separate verification pass in the old methods.
It's a night and day difference in terms of speed and cost. Verification becomes almost free.
We should also quickly mention they used class-level loss reweighting.
Ah, yes. That's important during training. You usually get way more wrong answers than right answers in the training data.
Right, it's imbalanced.
So reweighting the loss ensures the model doesn't just get lazy and predict low confidence all the time, because that's statistically common. It helps maintain a balanced ability to identify both correct and incorrect solutions.
Okay, essential housekeeping for robust training. So let's get to the results. How well did LaSeR actually perform? Let's start with reasoning, like math problems.
On benchmarks like Math 500 and AIM, which are standard math reasoning tests, LaSeR consistently improved the model's accuracy.
You have numbers.
Yeah. For example, models based on OctoThinker went from about 30.8% average accuracy using older RL methods up to 32.8% with LaSeR, a solid couple of percentage points, which is significant in these hard benchmarks.
Okay, better reasoning is good. But the main event was the self-verification, right? How well did it know when it was right or wrong?
This is where it really shines. The self-verification F1 scores, which measure how well it correctly identifies both true positives and true negatives, basically were hitting around 80%.
80% F1? That's really high for an internal signal.
It is. The Quinn 2.57 billion parameter model, trained with LaSeR, reached an average F1 of 79.6%. That's remarkably good self-assessment.
And this leads to that comparison that really caught my eye, comparing this built-in verifier to external ones.
Right. The amazing part is that this self-rewarding capability from LaSeR, even in a smaller model like a 3B or 7B, didn't just beat external verifier models of the same size. In some tests, it actually matched the performance of dedicated reward models that were way, way larger, like 72 billion parameters large.
Scat! So a 7B model with LaSeR has the verification chops of a separate 72B verifier.
In certain scenarios, yes. That's the potential here. You're getting that massive verification power baked right into the generator model, essentially for free at inference time.
That's a huge deal for anyone deploying these models. The cost implications are massive.
Absolutely. And it has direct practical uses. At test time, say the model generates 5 possible answers to a question.
Okay.
You can use the confidence scores for each of those 5 answers to rank them, or even better, to do a weighted vote.
Ah, so instead of just majority wins, you give more weight to the answers the model itself is more confident about.
Exactly. They called it RM at K for reward model weighted voting, and showed it significantly boosts the final answer accuracy compared to just simple majority voting, MAGE at K. The model helps you pick its best guess.
Okay, so for math reasoning, LaSeR looks like a home run. But what about broader, more general reasoning tasks? Did the magic carry over?
This is where things get a bit more nuanced. On general reasoning benchmarks like MMLU Pro and GPQOA Diamond, the self-rewarding F1 scores were lower, still decent, but more in the 65% to 70% range.
A noticeable drop. Why do you think that is? Is LaSeR itself less suited to general knowledge, or is it something else?
It's likely a combination of factors. One possibility is that the model's underlying reasoning ability on these very broad, sometimes ambiguous topics isn't as strong or clear-cut as in math. If the base reasoning is weaker, the confidence signal might naturally be less reliable.
Makes sense. Garbage in, garbage out, to some extent.
Or, perhaps more critically, the verifiers used to generate the initial tar-of-all signal during training for these general tasks are probably much noisier and less perfect than math verifiers.
Ah, right. Math answers are usually definitively right or wrong. General knowledge can be fuzzier, and the truth label might be debatable itself.
Exactly. And if your training ground to match a noisy dollars using that MSE loss, the resulting self-confidence signal is inevitably going to inherit some of that noise and be less accurate.
So the quality of the initial teacher, the verifier, really limits how well the student, the LaSeR score, can learn.
It seems that way, yes.
Yeah.
Okay, so looking forward, LaSeR currently costs at most 1 extra token inference, which is amazing, but
They want 0.
that's the ultimate goal, yes. 0 additional inference cost.
How on earth would that work? You have to calculate something, don't you?
The idea is to look at the probability distribution right at the very end, specifically at the end of sequence, EOS token position.
So before the model even outputs the I'm done signal.
Kind of. The idea is that in the probability distribution for that final step, just before stopping, the likelihood assigned to that pre-specified special confidence token should already reflect the model's confidence. You just read it off, that final distribution.
Okay, conceptually neat. Why didn't they just do that from the start? What's the catch?
Stability, mainly. They found that if you try to measure it right at the EOS position, sometimes the model might actually choose that special confidence token as the most likely next token.
And then instead of stopping, it might try to keep generating after the confidence token.
Exactly, which messes up the whole process. You need very careful control masking, perhaps to ensure that high probability for the special token acts only as a confidence score and never accidentally triggers further generation.
Yeah.
Technically tricky to get that balance just right.
A fine line to walk.
Definitely. So wrapping it up, LaSeR is really a novel approach. It cleverly unifies the ability to reason with the ability to self-assess based on this cool theoretical insight about the last token's predictive power.
And it delivers that with incredible efficiency gains.
High verification performance, high efficiency. It tackles 2 major problems at once.
It really makes you think, though. If they achieve that zero-cost goal, getting the confidence score just by looking at the final probabilities before the EOS token, it implies the model packs its final judgment into that very last moment. So the question I want to leave you, the listener, with is this. If a model can embed its confidence about complex math into the probability of one specific token right before it goes silent, what else might be hidden there? What other signals about its internal state uncertainty, maybe even bias or things we haven't even thought of, might be encoded in those final output probabilities, just waiting for us to find the right way to decode them? Is that final moment the key to the LLM subconscious? Something to ponder. Join us next time on The Deep Dive.